辛苦。
All right, so good morning, everyone. Hope you had a nice long break. Excellent. Okay, so today we're going to start the chapter on plasticity. I've already posted the notes on eClass, 5 notes for this chapter. Also, your assignments, the first assignment that is due next week, you should read the assignment off the notes. At the end of the notes, you're going to find some exercises. Your first assignment is actually the first problem. So I would say, just because I added a hint in the typed notes, so look at the first problem in your set of notes rather than in the assignment itself. It's the same problem exactly, but I just added a small hint in question D. So plasticity, we're going to divide plasticity into 3 vectors. In the first lecture today, we're going to cover the following. Physical observations, traditional isotropic hardened walls, in uniaxial and multi-axial stress states. So this will be lecture 1. Lecture 2, we're going to give examples on traditional isotropic hardening models and some hints on the assignment. Lecture 3, we're going to explore what we call kinematic hardening. Now, everything that we're studying here applies to plasticity of metals. The geotechnical group studied the plasticity of soils, which is slightly more complicated than the plasticity of metals. Now, the plasticity of metals is a very successful material model. It's perhaps the most successful material model. It's right after the linear elastic material model. The nice thing about the plasticity model is that it's very, the plasticity of metals in particular, that it's very, the equations might look difficult or complicated, but they're very easy to implement in a finite element analysis, and the results are very good, and they are successful in the design of any metallic component. And the reason of success lies in the fact that metals are very ductile. Because metals are very ductile, so you're able to model, you're able to take the strain up to large amounts, and the stress is still increasing. Now, when you look at the plasticity of soils or plasticity of concrete, these models are probably slightly more complicated because you don't have this ductility in the material, and so you end up with instabilities right away because you end up with something like that, and perhaps the behavior after the peak goes down, and so it's really very hard to model. When you try to model concrete or soils in a finite element analysis model, when you try to model their peak behavior, you will run into lots of difficulties because of the brittleness of the material. Okay, so that's the first thing that we want to talk about today is what are the physical observations. So I'm going to follow the numbering in the notes. So, physical observations, when we get a metal specimen and apply sigma on 1 and simply measure delta and plot sigma on 1 versus delta over L, which is the small string epsilon 1, you get the following behavior in general. I'm just exaggerated the slopes here just to distinctly divide the relationship into particular regions. In the first region, from point O to point A, the relationship between sigma on 1 and epsilon 1 is linear. The more you increase sigma on 1, epsilon 1 increases linearly, and for steel, you have the slope always given around 210 gigapascal, and varies according to whatever metal. For aluminum, you've got a different metal, and you got a different Young's modulus, but for all the steels, you get 210 gigapascal, or around. So, at any point between O and A, if this is the undeformed specimen, you apply sigma on 1, and then you remove sigma on 1, the specimen goes back to its original shape. And not only this, between sigma on 1, the relationship between sigma on 1 and epsilon on 1 is linear. There is another point, B, where the relationship becomes slightly nonlinear. However, it's still elastic because if I apply this stress, and then if I remove that stress slowly, I follow the same curve, and I obtain the same initial. I go back to the 0 position. And usually, point B and point E are point B and point A are very close to each other. The ends of the linear part and a slightly non-linear portion, they're usually very close to each other, and in all the models they're assumed to be the same point. In any theoretical model, point A and point B are assumed the same point. And traditionally, in mild steel, when these experiments were done on mild steel, what was noticed is, at some point, as you're conducting the experiment, as you're applying stress on the metal, all of a sudden, at a certain stress, there's a little bit of instability in the specimens. All of a sudden, you have the same stress, but the specimen is just extending on its own. And from point B to point C, that's the term. The material is yielding. It's basically, it is not offering any kind of resistance. You have the same stress, and it's just slowly extending. And so you have an increase in the strain without any increase in the strength. And after a particular amount, the material starts all of a sudden to get back its strength. So it starts back resisting the force that you're applying, and that's why we say it starts now to harden. It's becoming a little bit stronger than in the yielding phase. So now this is called strain hardening. And so from C to, let's say, point G, there is an increase in the, in order to increase the strain, I have to increase the stress until I reach a point in which the material starts to neck the specimen. And becomes very unstable. It doesn't take much to break. And the stress decreases while the strain increases. Now the area from C to G is called strain hardening. The reason why it's called strain hardening, even though you can see that the slopes, the slope here is less than the initial slope. So you'd expect that this is a softer material rather than a harder material. If something has a lesser slope, the relationship between the stress and the strain has a lesser slope, you would want to call it softer material, not harder material. But we call this hardening because this is hardening compared to the initial yield. What's happening here is that if I call this, and we'll explain why, if I call this the yield stress, the more I increase the strain, the more the yield stress increases. Because the yield stress is increasing, that's why I'm calling it hardening. Because that yield stress is increasing the more I apply strain compared to the yielding portion where the yield stress is not increasing when I apply strain. And so that's why this portion is called strain hardening. The difference between an elastic material and this curve is the fact that the material, this is the curve, whenever you remove the stress, so from this portion up to this portion, this is the original specimen, and then I apply sigma 1, and then I remove sigma 1, you'll find the specimen is a little bit damaged, does not go back to its original position. But there is a residual delta. I'm going to call this delta B. Now, I'm going to call this delta E. Now, from this point to this point, all I need to do is apply that value of sigma on 1, and then remove that sigma on 1, and I'm going to be able to elastically deform that specimen from this point to this point. So first I apply sigma on 1. So on the curve, it will look like this. Let's say I'm at this point. The moment I remove sigma on 1, I'm going to find the relationship between the sigma on 1 and the strain follows the same slope as the initial slope. So you deform the material into a new state, and then in that new state, the material is still behaving elastically, but it's just that its zero state has changed. Instead of this being its zero state, now this point is its zero state, or zero stress state. And so, at any point beyond the initial yield, the relation that the material still behaves elastically when I when I unload, and the moment I load, I'm still following the same slope until I reach this new sigma yield, and then the material starts behaving plastically again. And the moment, and so the material starts behaving plastically again. And what happens is, as I apply plastic strain, or as I apply stress or increase the stress and develop more strain, the sigma yield increases. And if I decide to unload at this point, then I'm unloading following this line, and loading following this line, with the same slope E. But what happens now is that my yield stress is higher. So this was 100, this is now 110. And you can see that the yield stress has increased compared to, so sigma yield 2 is higher than sigma yield 1. And that's why we also call it strain hardening. The more plastic strain there is, the harder the material, or the harder the yield stress. That's why this portion is called strain hardening. Now there are variations of that stress-strain curve, depending on the alloy, depending on the materials. Mild steel used to look like this. The very first experiments that were done, you get mild steel looking like this. So you really see this distinct yield phase. Now manufacturers and engineers realized that this is really not a very good behavior, this distinct yield phase. It's not a very good behavior because it's a point of instability for the material. You don't want this point of instability if you're applying this. If you're using this for a structure and all of a sudden you hit that load, then all of a sudden you're going to get the material will yield. And so the newer alloys don't have this kind of behavior. Newer alloys, some of them might look like this, and others, especially high strength steel. Especially high strength steel, you'll find when you plot sigma 1 versus epsilon 1, you'll get something like that. Again, this is the elastic region, and beyond that, if you unload, you follow this point, and this is a residual plastic stream. So the next thing from physical observations we want to know is what happens if I do stress, if I reverse the stress. So Boeschinger effect. So traditionally, for mild steel, you get the following. If I plot sigma on 1 versus epsilon on 1, and if I start to unload at this particular point, then this becomes my new yield stress. If I load again, the material is going to behave elastically from this point to this point. Now what happens if you actually now reverse the stress? So you have a slightly longer specimen. So you loaded the specimen, became a little bit longer, but now it's behaving elastically. Below the sigma yield, it's behaving elastically in the tension. What happens if you apply compression? If I apply compression from the initial point, if initially apply compression, I get the same behavior. Now, of course, you have to be very careful if you're doing a specimen in metals to not buckle that piece. You just have to apply compression and without buckling of that specimen. Now, if you unload from this point and then start applying compression, you'll find that this is also sigma yield, which means that the yield stress in both the tension and compression has increased. So hardening of the material happens for the traditional steels. Hardening happens in all directions. If you increase the yield stress in the tension, you've increased it in the compression. You increase the yield stress in the direction of sigma on 1. You've also increased the yield stress in the direction of sigma 2, and in the direction of sigma T3. So you've made that piece that metal piece, it has a higher yield stress in all directions, whether it's tension, compression, sigma on 1 or sigma 2 or sigma 3. This is called no Boeschinger effect. The Boeschinger effect, if the specimen has what is referred to as Boeschinger effect, if this is the behavior in tension from a zero state, and if this is the behavior in compression from a zero state, if I load the material so that I increase its yield stress in tension, now the yield stress in tension is higher than the initial yield, and then I start loading and unloading. Start loading and unloading, it will follow this curve, Now if I start loading in the compression, it's going to start yielding early. And this is sigma yield in tension. This will be sigma yield in compression. And it's smaller than sigma yield in tension. This is called Borschinger effect. And the mathematical model that models those two, which we're going to study, this is the mathematical model is called isotropic hardening. There are many models that can model the Borschinger effect. Each one has its each one models a specific type of Borschinger effect. You have kinematic hardening, bind, and kinematic isotropic. And in the third lecture, this will be the focus of what we're going to study. This is what we'll study in the third lecture. Now, yes?
Just a question, I think I missed it. So, typical mild steel exhibits no Borschinger effect, right?
Yes. That's because the stresses don't really increase that much. Because the increase in the yield stress here is not that high. For high strength steels, you get more Borschinger effect because the difference between this and this is much higher. Okay. Now there are many. We're not studying. If a person with studying metallurgy would try to explain these behaviors because of the crystals of the metal, but this is not the objective of what we're doing here. What we're doing here is that I have a physical observation, and physical observation has to do with something that's happening in the crystals of the metal, the yielding and all this. But what I'm trying to do is I'm trying to come up with a mathematical model that I can implement to predict the stress and the strain behavior of a material made out of this. Another important physical observation if this is the original state, and then I apply sigma 1 up to a yield point, a higher yield point, and then I unload, and this is my new zero state. Initial volume is equal to the new zero state volume. Which basically means that the development is such that delta epsilon P11 is equal to or plus delta epsilon P, the plastic strain 2 plus the plastic 3 is always equal to 0 for metals. That's not true for any other plasticity, but for metals, the change in volume is 0 as you develop plastic strains. And so this tells me the following. In a uniaxial stress state, and if the material is isotropic, delta epsilon plastic 2 will be equal to delta epsilon plastic 3, which means if I have a square specimen, as I increase it in one dimension, it's going to decrease in the other 2 dimensions, such that the plastic strain 2 and the plastic strain 3 will be equal to negative delta epsilon P1 over 2. Now, some books call this the Poisson's ratio of half. We can't do that because Poisson's ratio, we cannot call this material having a Poisson's ratio equal to 0.5. And the reason is Poisson's ratio is only applicable to linear elasticity. And in linear elasticity, we've studied that the Poisson's ratio cannot even reach half. If it reaches half, the material becomes incompressible. And so this is a different material model. We're talking about plasticity here, so we can't use the term Poisson's ratio to describe this behavior. Okay, so let's now try to understand how to mathematically model all this. So what we described is something that we noticed in the lab. There's no math at all. This is just things that we took a specimen to the lab, and this is what we found. And the first item that I want to talk about is the yield stress. The definition of the yield stress. Whenever you look at any of the codes of practice, they specify, they tell you the yield. This is a steel with yield stress 360 MPa or 650 MPa. So how do you define the yield stress of the material? Now, depending on the material, for the mild steel, it's simple to define the yield stress because you have this region where the strain is increasing, but the stress is not increasing. So you can define the stress as the average of this region, or however you want to define it. You can define it as the maximum point before it drops, or the lower point. You've got upper yield, lower yield, however you want to define it. But they're all very close to each other. If you have a different alloy, where all of a sudden it's a really gradual increase, it's really difficult, or the yield stress is not really well defined. There's not a particular point where you can say, this is the yield stress. And so there are two different, depending on the code of practice, there are different definitions to find the yield stress from the stress strain behavior. And so traditional steel codes adopt the 0.2% offset. If you want to find your yield stress, take an offset 0.2%, and draw a curve. Draw a straight line, and where it intersects, call this your yield stress of that particular material. The pipeline code, the CS, so this is, I would believe this would be the traditional CSA code for steel. The CSA code for pipelines define yield as take 0.5% and check vertical, and this is your yield stress. So it really depends on which code you're looking at. You might find different definitions of what your yield stress is. The ultimate stress is really well defined. That's the maximum stress that the material can reach. And the ultimate strain is the strain corresponding to the ultimate stress. So these are well defined. Yield stress is not very well defined, and that's why you get this 0.2% or the 0.5% offsets. So there are different idealizations for the stress strain curve. So first of all, in everything from now on, we're using the true stress versus true strain. The theory is developed for the relationship between the true stress versus true strain. So if you, this is the behavior. As you load and unload, you follow this curve. And there are different idealizations. There's one idealization is, which applies mostly to mild steel, is elastic, perfectly plastic. If you're doing a hand calculation, which you probably don't need to do anymore, but if you're in a consultant office and an old consultant who does a lot of work with metals, they probably like this model where I don't really care about how much the stress increases beyond the initial yield. I'm going to assume that the stress is not increasing and the material behaves in this elastic, perfectly plastic. Now all the plastic hinges that you study, if you ever studied plastic hinges in metals, in structural analysis, most plastic hinges assume elastic, perfectly plastic because you can just assume the stress is never going to increase, but the strain can increase. So when you have a plastic hinge, and you apply sigma at a moment, you assume that the stress never increases. So you assume this kind of behavior, if you ever seen this before. Where this is a beam, you have your tension, you've got compression, and you assume that it would be much easier to assume that this is perfect. In plastics, the stress level increases. You have a region of elasticity and everything else. Plastic, this is much easier to calculate by hand. And in the limit, you get this block and block. This block and this block. So it's it's much simpler to calculate the moment based on that rectangle rather than a curved surface. Another idealization. Linear hardening. It's really not a very big deal if I just approximate this curve with a linear curve, especially that the increase between this and this, if you actually test another specimen, you're going to get a totally different curve. So to get a totally different curve does not warrant that you have to be that precise in describing the curve, because the difference between one specimen from one portion to another specimen from another portion of the same metal, you're going to get totally different behavior. Not totally different behavior, but I'll give you just visual examples. So these are just the same piece or the same block of materials. I'm grabbing specimens from different locations. You'll get things like this. And so you can group them all and pick just the horizontal line to describe all these. So in a uniaxial stress state, this is what we do. First, this is the true stress versus the true strain. At any point, we know that as we increase the stress, there are two components for the strain. This is epsilon 1 elastic, and this is epsilon 1 plastic. Now, epsilon 1 elastic is equal to sigma 1 over E, because the elastic strains are related to the stresses using the linear elastic constitutive law. And the plastic strain is equal to the total strain minus sigma 1 over E. And so it makes sense to draw the relationship between sigma 1 and epsilon 1 plastic. The relationship between sigma 1 and epsilon plastic, at the before the initial yield, there's no plastic strain. So I'm going to call this sigma yield 1. So as the stress increases from 0 up to sigma yield 1, nothing happens. The moment the stress increases beyond sigma yield 1, you start developing plastic strain that's equal to epsilon 1 minus sigma 1 over E, so you end up with a curve that looks like this, where this is the relationship between sigma 1 and epsilon 1 plastic, or you can look at it as the relationship between sigma yield and a plastic strain parameter, epsilon. Because at any point, this point on the curves describes to me the following. Given epsilon P, what is the yield stress in the material? So now I know what the yield stress is. Let's say this is sigma yield 2. So I'm at this location right now. I'm behaving in a linear elastic manner between sigma yield 2 in the tension and sigma yield 2 in compression. So now I have sigma yield 2. The sigma yield 2 is the yield stress of the material. And the amount of plastic strain inside the material is equal to this parameter epsilon bar P. If I decide to load the material higher than sigma yield 2, then I'm going to develop additional plastic strain. Corresponding to the new sigma yield 3. And now this describes a new stress state, or a new state for the material, where the yield stress is sigma yield 3, and the amount of accumulated plastic strain inside the material is epsilon plastic 3. This relationship between sigma yield and epsilon P can be described so it looks like this. There are different material models that can be used to describe this curve. As we said, you can have the kinematic the linear hardening. We can assume that this increases linearly. You can assume that this is perfectly plastic, or you can use what is called the Ramberg-Osgood approximation. The Ramberg-Osgood approximation approximates this curve with this curve. This red curve, sigma yield, is equal to epsilon R over K E R 1 over N, or epsilon P bar is equal to K sigma yield over E R N, where N and K are constants that you obtain from curve fit. And the subject, third question in your assignment is to find n and k for a curve that is in your assignment. And to find n and k, you can use, there are different functions in Mathematica that you can use to fit data to a model. So I give you a few hints which models, which functions you can use. But it will be easier to try to fit this rather than trying to fit this. So fit the data that you have to this relationship. And do not include the initial point, because the initial point will cause issues. Okay? Okay, so I'll give you 5 minutes, and then I'm going to start we'll start talking about the different things that we want to talk about.